Hello, everyone. I'm Jin Fan from New Jersey Institute of Technology. So today my presentation topic is about numerical simulation on the cracking effects and chloride concentration on the corrosion behavior of normal reinforced concrete. Here is the presentation outline. First, I'm going to introduce background information as motivation of this study, and then present some of the preliminary results on the chloride distribution in the reinforced concrete. And after that, we can proceed to the corrosion behavior. For example, here we are going to focus on the corrosion current and end this presentation with a short summary. Background and information. As we know, for the normal reinforced concrete, there might be many durability issues. Among those durability challenges, I think corrosion is the primary causing mechanism of the durability issues in normal reinforced concrete. For example, the bridge deck we see here, especially when there is an initial cracking exists, and we apply when we apply de-icing materials, and the corrosion is likely to happen. So what we want to really figure out here is what's the impact of the crack width, and also how the corrosion behaves differently if we apply different surface chloride concentrations. So one very straightforward method is, of course, conduct the long-term durability test. And maybe another approach is to use the numerical simulation. Here, let me introduce lab testing conducted by one of my colleagues who couldn't come here. So this test is based on, we applied the ASTM G109 method, and first we cracked the beam. So we get a bunch of different crack widths, and then we apply chloride pounding as a cracking surface. And we also want to study use different brine concentrations at the cracking surface. In order to accelerate this corrosion test, we applied wet and drying cycles up to around 1 year. So in each cycle is 14 days. However, for this corrosion test, we have several limitations. And for example, the crack width is really difficult to control because of the size of the beam. And also each of the tests takes a really long time. So we wonder if we can extend this study with the help of numerical approach. With the numerical method, first we're going to replicate what we did in the test. So we're going to apply mechanical load so we can get the cracking information, and then apply this cracking information to conduct the next step study, which is to get the chloride distribution in the cracked specimens. After that, we can define the active corroding area, so we can continue the analysis and get the corrosion current. So with this numerical approach, we can first result we want to look at is the chloride content. The first one we are looking at here is the chloride profile of the 1.5% of the surface chloride concentration. The figure we are looking at here has a crack width of 0.18 millimeter, and the y-axis is a result of the chloride content measured in percentage of the concrete mass, and the x-axis is depth to the exposure surface. We may notice in the first layers close to the surface, the numerical results is underestimated the experimental test. This is because close to the surface, it is a convection zone, which is kind of tricky. But our concern is really is about the chloride chloride contents close to the steel surface. For example, we see here up to 26 millimeter, where is the rebar located? We have a pretty close chloride prediction to what we get in the test, and is also conservative. So on and so forth, we got a similar trend with 3% surface chloride ponding condition, and also for 4.51 and 6% one. Here we used a different crack width because we want to compare the result directly to what we get from the test. And same with the 9% one. So we got all this, like a series of this test and numerical simulation result. What we really want to figure out is what we get here is we can say the numerical approach provide a pretty reasonable accuracy in predicting the chloride content, especially at the steel surface, which is particularly to our interest, and also is effective even in this condition. We applied wetting and drying cycles. So if we plot all this like a series of different chloride concentrations and crack widths in same graph here, we can see, for example, if we look at a specific surface chloride concentration, for example, at 1.5 surface chloride concentration, actually the slope here we get is relatively small. However, with other concentrations, for example, at 9% one is much bigger. So this means the crack width actually has less impact when the chloride surface chloride concentration is low. And also, if we look at a specific crack width, for example, the chloride content, increases fast, like at 4.5 and 6% surface condition, which means like is the result. The chloride is more influential at these two concentrations compared to the others. So after we get the chloride distribution in the concrete, we can continue with the next step study and conduct the corrosion analysis. The result we get here, first we are looking at is 1.5 surface concentration one. So this is a corrosion current versus exposure time. And we have different crack widths, and first is 0.18 millimeter, second is 0.32, third one is 0.59. We see like jumping up and down of this result is because we applied wetting and drying cycles. So when we add the solution, the corrosion current is higher. When we remove the solution, it drops down. And the scattered data here is the test result. And actually, we didn't see much from the corrosion from the test. It possibly because self-healing of the concrete, or just because of the variability of the test result. We have a limited number of specimens tested. And another observation is like we can see the corrosion actually increasing fast within like 200 days. And after that, it starts to stabilize. It's not increasing like significantly after a certain time. And also from crack width of 0.18 to 32, actually the increasement of crack width is kind of big. However, we didn't see the corrosion. The corrosion itself is increasement is not proportional to the crack width. As we see here, the gap is relatively small between the 0.18 millimeter crack width and the 0.32. So we can say the critical crack width for this specific chloride concentration is between 0.3 to 0.6 millimeter. And the same trend is observed with 3.3% surface concentration one. And still we observe the same trend, like when we have the initial crack of 0.18 millimeter, actually we see a significant amount of corrosion. However, when we increase the crack width, it's not increasing proportionally, it's just slowed down, and it's shown in this figure as the gap between these three different crack widths is getting smaller. And we have like a similar trend with 4.51. The difference is like the corrosion stabilized faster. And the 6% one, same. Here the crack width is from the test is 0.3. And the 9% one. So what we really want to figure out is the impact of crack width. From this series of simulations and tests we get, we can observe that actually the impact of crack width itself is limited, because when we have an initial crack of 0.18, we see a significant amount of corrosion. However, when we increase the crack width, the corrosion itself is not increasing proportionally, it's just and now we want to look at it into another factor, which is surface chloride concentration. So when we plot the different chloride concentration conditions and the same curve with under the same crack width, and we see like from 1.5 to 4.5 like surface concentration, the corrosion current is increasing like almost proportionally. However, when we get higher chloride concentration at surface, actually, again, it slows down, and the gap between these different crack widths, especially at higher concentrations, is getting smaller. And the same trend observed with the 0.32 millimeter crack width one, and also 0.59 millimeter crack width one. So what it tells here is, like, as we know, of course, we get like higher corrosion possibility when we have like higher chloride concentration. However, the relationship between these two is not linear. Is the impact of surface chloride concentration is actually limited when the concentration is high enough. So here are some takeaway from the simulation results. And corrosion status started to stabilize at some point, and it stabilized faster when we have a bigger crack width, and also it stabilized faster when we have higher surface chloride concentrations. But what really the key factor here is the initial cracking itself is not the crack width. And crack width has a limited impact on the corrosion propagation, which is kind of counterintuitive. And also the impact from the surface chloride concentration is limited, especially at high surface concentrations. So, and here's the summary. from this numerical approach, we can say is very effective in quantify the corrosion performance, and through this numerical simulation, it confirmed that the impact of crack width and surface chloride concentration, and the corrosion started stabilized at a certain time. However, the impact from surface chloride concentration and crack width is kind of counterintuitive to what we think, and is actually limited in certain conditions. And yeah, that's it. Feel free to ask if you have any questions.
All right, thank you for your presentation. No? All right, I have a question actually. So specifically the numerical modeling you have used, it is a specific model that you have used, or it is like a specific software you used to model this? I just want a little bit know about that model you have used for modeling.
Okay, so the framework is actually, so we want to get the crack information first and then study the chloride distribution and then conduct the corrosion analysis. We used a bunch of different computing platforms. Just for the cracking behavior one, we used one, and then we applied the result to the and as input for the next step study in another software. Actually, there are different ones involved.
It was like a machine learning algorithm involved or not?
No,